Okay, let's continue. So in the last class we looked at SAR ADC. Again, let me just switch off the slide. So the basic idea of SAR ADC was that we decided that instead of doing a flash, wherein we use multiple comparators, we decided to use only a single comparator and do this job. And the efficient way to do this was through binary search. So for doing n-bit conversion, you have to do a total of n comparisons. And this basically, we saw that it's essentially a negative feedback system, right? And we saw one of the common implementations in the recent times, and that is done using the capacitive structure. And remember that the whatever you have in the feedback that takes in a digital output 1 or 0 feeds back an analog voltage, so that acts like a DAC. So we used a capacitive DAC, and where is it? Yeah, and in a 2-bit SAR we saw that capacitors are arranged in a binary weighted fashion. So you start with 2 times C. For a 2-bit it's done. Similarly, for a 3-bit case you start with 4, 2 and 1. And the way we operate is, initially we put in an initial condition of Vin minus Vref across this entire capacitive array, and then we keep switching appropriate capacitors to ground to generate the required reference voltage. And yeah, and the logic we had was the following: in every step we ground the kth capacitor, and if the previous comparison was 0, we were actually flipping the previous capacitor back to Vref. And then we did the differential case, and finally we actually recognized that right now we are doing 2 steps: grounding kth capacitor and flipping k-1 capacitor back to Vref. The observation was, every time you switch a capacitor to ground or to Vref, you are burning power. So we decided to avoid this extra step of flipping back to Vref, and that gave rise to the monotonic switching scheme. Where is it? Yeah, and here the logic is pretty simple. You just, at every step, you look at the previous comparison output. If it was 1, you flip the capacitor in the positive side to 0. Otherwise, you switch the capacitor to ground in the negative side. Only one capacitor you switch every time. Okay, cool. So this is the logic we know. Now, of course, we have to make sure that this is also done automatically. That is, as of now, we know in sampling phase circuit should look like this. When you want to compare with Vref by 2, it should look like this, and so on. This should also be automated, because we can't send one engineer with every ADC and say he'll switch this and that, right? So let's see how we can actually do that. Oh, sorry. Yeah. So okay, let's list down the operations we have to do in a SAR, right? First we sample the input, right? And how many times I do the comparison? N times. So total of how many operations I'll have to do here? A total of roughly n plus 1 operations. And remember, all these n plus 1 operations must get over within the clock period of Ts. Right? So which means, what would be a natural thing for you to, what would be a natural time you can allocate for each of these operations? Let's say you divide it equally, so Ts by n plus 1. So in the olden times, the way this was accomplished was like this. To the ADC, you fed in a high frequency clock like this, whose time period was Ts by n plus 1. So this is a clock at n plus 1 times Fs. So this way you clearly know when to do which operation, right? The first clock cycle you do the first operation, second clock cycle you do the second operation, and you finish it. So this is now what is referred to as the synchronous SAR. Because as you see, each operation is done in sync with this clock edge. We have specific time instance at which we start one operation in one operation. Okay. But of course, here let us say you are looking at a sampling speed of 1 kilo samples per second. and let's say you want to get 10-bit resolution, what will be the clock I'll have to feed into the ADC? 11 kilohertz, right? But this is okay for low speeds, but let us say you want to do it at a higher speed, say 100 megahertz. What will be the corresponding clock frequency you'll have to feed in this case? 11 times is 1.1 gigahertz, which obviously seems like a difficult thing to do, right? So because of this, for a very long time, SAR was always treated as a low speed ADC. But later is when people recognize that instead of having to feed in this high frequency clock and then do these operations in a synchronous fashion, we can do all these n+1 operations in an asynchronous fashion, right? That is, as of now I need this clock to exactly define when to start each operation, right? So the idea is we do some kind of self-timing. So we start the first operation, detect when that is getting over, start the second operation, detect when it is getting over, and keep doing that in a cycle. So let's see how we can do that, and this is what we do now, and this is what is called as asynchronous SAR. Okay. So again, the exact implementation of this asynchronous business will depend on the kind of switching scheme we have for the capacitors. We'll just look at possible implementation for the monotonic switching scheme we have, right? And let's again list down the sequence of operations we have to do. So first, obviously, we sample the input. That is non-negotiable. And in a differential SAR, where the input can be from minus Vref to plus Vref, what is the first reference with which I compare the input with? 0. Comparison with 0, it simply means I compare the positive versus the minus input, I see which is greater. This is first comparison. And once the first comparison is done, I'll just see if it's greater than 0, I'll check with Vref by 2 and so on. And we also know the logic for that from the monotonic switching scheme. Wherever is it? Yeah. The logic is this. Based on the previous bit, you flip the capacitor in the positive or the negative side. Right? So the logic we have to follow is this. If the previous comparison was 1, you connect the kth capacitor in the positive side to ground, else kth capacitor in the negative side is grounded. So once you do this, you generate the required difference, V in minus whatever k Vref by 8, something is done. Once this voltage is generated, what should you do? When you have generated the voltage, what should you do? You should compare it after this, right? So we run the comparator, and then what should you do? We have to keep repeating it, so you'll have to repeat this. Again, remember this is the first comparison, so I'll have to do this for n-1 times. This is roughly the sequence of operations we'll have to do. Okay. So let's see how we can go about doing this. Okay. So first operation is sampling. So let us say I feed in a sampling clock like this. Something like this. Okay. So this time is Ts. This time period can be equal to Ts by 2, Ts by 4, but I'm just drawing it in a slightly, like skewed fashion so that I have more time here. Okay. But this typically can be half the clock period or 1/4 the clock period, depends on the situation. Now first, when you are sampling it, you have to sample the input. So what I'll do, I'll lump all the capacitors we have into a single capacitor. Similarly, in the negative side also I have all capacitors, I lump them. And I'll have to sample the input. So I have a switch here. This is running at 5S. So the top side is Vi plus. So sampling is trivial, done. So after sampling, I have to compare the inputs. So I need to connect this to comparator. So let's say I connect it. So this is, let's say, the positive and minus output of the comparator. Now let's figure out, so we are sampling the input when phi s is high, right? So when can we start the comparison? When? After phi s goes low, right? And remember, all our comparators are all clock comparators, which means in one clock phase it starts the comparison. In the other clock phase, what happens to the outputs? Huh? In the strong arm latch, what we are doing in one clock phase? Yeah, I mean one clock phase we compare, but before that, what do we do? Yeah, pre-charge to VDD, right? So we have a clock comparator. So let us say this is the clock. I'll say phi reset. When this clock is high, I'll say the comparator is reset. That is, it's getting pre-charged. So, which means what clock can I feed for phi reset now? When this clock is high, I should reset the outputs. When this clock is low, I should start the comparison. So what can I use for phi reset now? Same as?
Yes.
Phi s. Okay. When this is high, I'm resetting. This is low, I'll start the comparison. Right? So let's say I'll call this to be phi s as of now. So even the phi reset clock will look the same. So the moment the reset goes low, the comparator will start comparing, and let's say after a short while it finishes its comparison. The first comparison is over here. Now remember, this step is done. Now we can start with these steps. But one thing to notice, every time we fire a comparator, we get 1 bit. So we should make sure we store that bit, because next time we're losing it, right? So to store this digital data, what do I use? Register. It's a flip-flop. So essentially I need to use a flip-flop here. Let me demarcate this. Let's say it's a D flip-flop. And what should be connected to the D input of the flip-flop? The output of the comparator. Let's take the positive itself. Anything is fine, right? Now similarly, for, let's say it has a n bit SAR, I'll have to have how many flip-flops? N of them. So let's say this is the second one, third one. So remember, all of them will be connected to the same D input. So let's say this is the first MSB D1, this is D2, D3, and then you have so much. Okay, so now I see that the same signal is connected as the D input for all the flip-flops. So how will I decide where am I storing the first bit, where am I storing the second bit, and so on? Remember, this needs to be clocked. Okay, so we'll give different clocks. Fine. Now one thing before that is, before you even decide to store the comparator output on the flip-flop, you need to determine when the comparator has finished making its decision, right? I mean, you have given the input, comparator is comparing, but how do you think we can decide when the comparator has finished its decision? Any thoughts? What is one time period here? Sorry? Yeah, remember, when I am resetting it, what happens to the comparator outputs? Both are pre-charged to VDD, both are 1. Once the comparison is done, this is what we have. So you have to detect this situation and give an output of 1. And what is one simple logic that gives an output of 1 for this case? XOR get or anything simpler? If one of the inputs is 0, output should be 1. Huh? NAND gate. Okay, XOR is also fine, but NAND gate is easier. So we put this NAND gate and then we'll generate, we'll call as a valid signal. So every time the comparator finishes making a comparison, this valid signal will go high. Fine. So here, let me also draw the valid signal. So at this point, comparator has finished its decision. So after a small delay of the NAND gate, the valid signal will go high. Cool. So now we have detected when the comparator has finished its decision. We have to store the data. For that we have to generate a clock. And remember, this clock phi 1 should go high when the first time the valid signal is going high. Okay. So which means we should generate a clock which goes high after the valid signal. So one way to generate this is, again, I'll just show it, it's pretty trivial. Take a flip-flop, connect its input to logic 1 and to the clock, feed the valid signal. Right? So first time valid goes high, D input is 1, it will go high. Right? So the sequence of operation we do is first you detect when the comparator has finished its decision to generate valid signal. Once that is done, using this valid, you generate the clock phi 1. That is step number 2. Once you have the clock ready, use it and store the data on the flip-flop. That is step number 3. Right here. Okay, cool. So now we have finished everything with respect to the first comparison. We sampled the input, did the comparison, figured out when the comparison is over, generated an appropriate clock and stored it. So everything related to the first comparison is over. Now we can move on to the step. So here I just have to switch the capacitors. So again the logic is this from monotonic switching. If the previous comparison is 1, the capacitor in the positive side is grounded, otherwise the negative side is grounded. So for simplicity I will draw only the positive side capacitor. So let us say this is the capacitor you are going to switch based on D1. So remember this plate is either connected to ground or to VREF, right? So how do you, so what do you put here? You put couple of switches. Just to remind, this is the positive side capacitor. So I have 2 switches, one connecting to VREF, one to ground. Fine. Now remember the logic says I connect the capacitor in the positive side to ground when the first comparison is over and when D1 is high. So what should be the control signal to this switch? I mean the logic is after the first comparison is over, after the first comparison is done and when D1 is 1 is when you have to connect it to ground. What do you want to give? Okay, D1, it might look as D1 but this will not suffice because if you just give D1 here, what can happen is the D1 is the output of the flip-flop. From a previous conversion cycle, D1 could have been 1, right? So from the previous conversion cycle, D1 could have been none and that could have grounded this. So it is not just enough to feed D1, should also detect when the first comparison is done. So which of the clocks here tells me when the first comparison is done? Valid and phi 1, but remember valid will go high every time you fire a comparator, right? So next time when you do the second comparison, valid will go high. So phi 1 is the clock, so you basically AND it with phi 1. So which means what should be the control for the other side? When this is not connected to ground, you connect it to VREF. Complement of that, right? Because when it is not connected to ground, you connect it to VREF. Simple. So okay, now time to replace ideal switches. So how will you implement this switch? NMOS switch. So let me do that. So this is D1 times phi1. This is ground. How about this guy? VREF is basically VDD, so that you do with PMOS. So the control signal to the gate will be complemented for the PMOS. So as of now it is D1 phi1 bar. To the PMOS I will feed D1 times phi1. So this is basically VREF. Fine. So this is in the positive side. Now similarly in the negative side, you have the same set of capacitors. In the negative side, you switch this capacitor to ground when D1 is 0. Right? So what will be the control I'll feed in the negative side? The logic says when the previous bit is 0, you connect the capacitor in the negative side to ground. Right? So again I have to detect when the first comparison is done and see when D1 is 0. So what might be the logic? D1? D1 bar times phi1. So same thing you feed here also. Okay. Cool. So now we have switched the capacitor. So which means you get the required voltages on the capacitor plates, V in minus whatever VREF. So next step is you have generated the voltage here. You fire the comparator. Now remember, the comparator has finished making its previous decision. So before you start the comparison, what should you do first? You reset. Again, life lesson from comparator, don't hold on to your past. Before starting the fresh comparison, you reset it. So which means as of now phi reset is only phi s. That is not enough. So I should feed some other signal which goes high after the comparator has finished making its decision. Right? And here you see it's the valid signal that marks when the comparator has finished its decision. So what you can do is the following. You can take this valid signal, I'll say delay it by few buffers, generate a delayed valid signal, okay, and feed that as the reset. So what we are doing is this: once the comparison is done, valid goes high. Okay. Now we are giving some time. This time is basically delay of the NAND gate and the delay of the buffers you have. After that time, you go and reset the comparator so that you start the next comparison. This is how we are self-timing it. Okay. Valid marks the end of the comparison. You give some time so that you can do all these operations. Which means after this time, you go and reset the comparator again. So what will happen is this. So let us say delayed valid goes high somewhere here. This is delayed valid, I am not drawing it. Okay. So delayed valid signal goes high somewhere here. So which means the reset signal will go high here. Fine. Now reset signal is going high here. So if the comparator is reset, what can you say about the outputs? They will be pre-charged to VDD. So what will happen now? Both are at 1. Valid will become 0. So which means valid signal will now come to 0. Now if valid comes to 0, delayed valid signal will also come to 0. So let us say after this delay it comes to 0. So which means the reset signal will also go low. So let us say at this point. So which means now we have reset the comparator and then taken it out of the reset. So it will start comparing the second input. and the inputs are already available on the capacitors. So now what will happen? Second comparison will be done. Let us say the second comparison is done somewhere here. For example, let's say at this point second comparison is over. So what will happen now first? Yeah, again the same sequence of operation. Once the comparison is done, valid will go high. So at this point valid goes high, and then you do the same set of things, right? So this is the first step. Now we have to generate a clock to store the second bit. Okay, so which means the clock for the second flip-flop should go high when valid goes high for the second time. So that clock should look like this now. Second time is where it goes. And again, it's not that difficult to figure out, that you can simply do it like a shift register. So you can do it like this actually. Oops. Just give me a second, make some more space. So this will be 5. Fine. So 5 and will go high after the first comparison is done, correct? And after the first comparison is done, when valid goes high, it marks that the second comparison is done. Simple logic. So we can get the clock pass. So you use phi2 to go and save the second bit here, right? And then you have the same set of switches. So you'll switch the corresponding capacitor and you generate the required voltage. Now remember, parallelly, this valid and reset will keep happening. So what will happen now is the following. Valid goes high, so the delayed valid will go high somewhere here. Fine. If the delayed valid signal goes high, what will happen? Reset will basically go high. So at this point, let's say reset goes high. When reset goes high, what will happen? Comparator is reset, the outputs are again pre-charged, which means the valid signal will go to 0. Okay. So now the valid signal, let's say, goes to 0 somewhere here. Valid signal goes to 0, what will happen? Yeah, delayed valid goes to 0. Yeah, we'll go step by step. So delayed valid goes to 0 somewhere here, which means this is connected to the reset. The reset will also go. So which means now we have reset the comparator, taken it out of reset. It is ready to do the third comparison. So once again, third comparison is done, valid will be generated. So once again, you have to generate the other clock so that you can do it the same way, right? So this is phi 3, and then you keep generating other clocks. Yeah. Which will, there are two sets, right? Vertical or horizontal? Okay, good question. He is saying, why don't I use this as a clock to this? Is that what you are saying? This as the input. No, remember that if you feed this as the input, the bits will get shifted, right? But no, that won't be good, right? Okay, I understand what you are saying. It's a clever suggestion. I understand what you are saying. It's a clever suggestion. But the issue is, this is assuming that the input keeps toggling. If let us say input is same. No, you are suggesting you feed this as a clock here. Why do you want to feed this as the input? Yeah, why do you want to shift it? Okay, you are saying, okay, right now the MSB is stored in this. Yes, that's also fine. I mean, right now the MSB will be stored here. MSB -1 will be stored here. If you do what you told, MSB will get shifted to the last. That's okay. You can do. That doesn't. You didn't. Which one? This one. This is still needed, right? This is required to trigger the flip-flop. You are suggesting, okay, understand. That's a good suggestion. So let's see. You are saying you feed this as you feed valid signal here itself, and then do this, and then you keep shifting it. Yeah, this should also be workable. Yeah, I mean, I'm not saying this is the only way, right? Just, yeah, as of now it seems fine, but yeah, we can see. But there is a reason we do this, I'll tell you. Because I'll come to this what you told. This might have one issue, I'll come to that. But as of now it's fine. Okay. So after third comparison is done, you generate valid signal, generate the third clock, store it, flip the capacitor, and then let us say this keeps repeating, right? So now third comparison is done, let us say somewhere here, valid signal will go high, okay, and then same thing repeats, and you do it for so many times. But two things we have to do to complete this fully. First thing is the following. If you just leave the circuit as it is, right? Let us say you are looking at a 3-bit conversion. After 3 times I finish the comparison, my job is done. But if I don't do anything, what will happen is this: after the last time valid goes high, that will again make the delayed valid go high, that will reset the comparator, right? So basically this will happen. So delayed value will go high, reset the comparator, which means valid will come low, reset will come low, comparator will again compare, and this will keep happening continuously. You understand the logic? Because the way we have self-timing the comparator is this: we detect when a comparison is done. After a delay, we go and reset and start the next comparison. So if you don't do anything, even after your last comparison is done, the comparator will be continuously triggered. Again, that's a waste of power. So which means after I finish the last comparison, what should I do to the comparator? Huh? Yeah, you want to reset it once the last comparison is done. So let me draw phi 3 also here. So basically phi 3 will go high, third time the valid signal goes high. So we have to reset the comparator once the last decision is made. And let us say in this case it is the third decision. Which signal here marks the end of the last conversion? Phi 3. So to reset it, what should I use now? I'll basically add phi 3, or in general the last clock. So this is the reason why we have to do this. Okay. If you do that way, you are right, it will work, but the comparator will still keep running. So you have to figure out some other way to do this. So we have to have some marker that says when my last comparison is done, and that is obtained in a clean way with this clocks. So fine. So one more last point, which is the following. Remember that these clocks, we assume that they are starting from 0 when we start the conversion, but now it looks like all of them are at 1. So which means in the next sampling phase they will start at 1. That is not something you want. So when the signal is getting sampled, what do you want to do to these clocks? They want it to go to 0, and these are generated by flip-flops. So what can you do? Yeah, flip-flops also have a reset pin, luckily. Let's say that is the reset pin, I'll just mark it as R. So what signal can you give to the reset signal now? Yeah, remember when I'm sampling the signal, I want all of them to start with 0. So which means I'll go and feed phi s as the reset for the flip-flops. That's all. So again, if I were to summarize it once again neatly, so let me first draw the capacitor. So let us say this is the capacitor, MSB capacitor. So this is basically connected to either the reference or to the ground using 2 sets of switches, and the control here is d1 times phi 1, d1 times phi 1, and then you have all the other capacitors in a binary weighted fashion. And in the monotonic switching scheme, we had the last capacitor C always connected to VREF. Same thing you will have in the bottom side. In the negative half also you'll have the same structure. PMOS connecting it to VREF, NMOS connecting it to ground. The controls will just be D1 bar times phi. Same thing you will do for the other capacitors, and then you finish this. And this basically goes to the comparator. And remember that we have to first sample the signal, so that will require two switches here. This is sampling the Vi plus and Vi minus, and this is the master clock we feed into the system, the sampling clock. Everything else we had derived internally and did that. Maybe I'll make some more space. So first thing we did was the following. We detect when the comparator has finished its decision. For that we ANDed them, generated what we call the valid signal, and then we had to store the information on a flip-flop. For that you have to generate appropriate clocks, and the clocks were generated in this fashion. So you feed in one and then gave the valid signal here. So this will give the first clock, second clock phi 2, similarly the last clock phi n. Right? So once you generate the clock, you go and store that comparator output onto a flip-flop. So that is also done using another flip-flop. Let us say this is the positive output QP, feed that here and give the clock phi 1, that will give the MSB, and so on for all of them. Okay. So again, once you store it, we have to fire the comparator again, and for that we did the following. Once the comparator has finished its decision, we waited for a short while and then fired it again, and for that we delayed this fellow, here, generated a delayed valid, and then we used it to reset the comparator. So the comparator is reset first time when we are sampling the signal, and every time we have finished making a comparison, we give a short while and then you start it. So delayed valid, and finally after the last comparison is done, you have to reset it once and for all, and that is done using. And again, the reset signal you generate it using this. You have to OR the 3. Same thing I'm writing, phi s, phi n, and valid delay. And one last thing is you have to go and reset the clock so that they start from 0, and you reset it at the sampling time. Okay.
So how do you ensure that the nth edge of phi n will come before the second edge of phi s?
Oh, that you have to ensure. And that's basically saying how can we ensure n comparison as
Nth comparison will happen before the.
Yeah, that you have to design and ensure, right? Basically, his question is how can I ensure this phi n comes before the next sampling edge. That boils down to the fact that how can I ensure that all n comparisons are done within time. That you have to design, which means you can't do like ultra high speeds, right? Depends on the delays you have, comparator delay you have, time taken for the capacitor to charge, everything that will impact.
come up to comparison delay plus the valid delay.
Correct, comparison delay, valid delay, but remember that by the time you should also finish doing these things. See, there are two things happening parallelly. Once every comparison is done, you store the data, switch a capacitor here. Now parallelly what we are doing, once the comparison is done, you are waiting for a while and resetting it again. So these two have to be properly thought of, that's all.
You are waiting for that much amount of time so that these two operation 3 and the last.
Correct, correct. Yeah, we have to ensure sufficient delay is there here. You tell me, right? Do you think it will be independent of the input? You should be able to answer it now. So let us say you have differential input to the comparator. If the input is if when in doubt you take extreme cases, right? Let's say input is really large. Let's say it's like 500 millivolts. And one point let us say input is 1 microvolt. Which of the two cases do you think will be easy to resolve? If the input difference is large, right? If the input difference is large, just by looking at it, I'll be able to say, right? So delay, comparator delay is not independent of the input. It in fact depends on the input. If the differential input is small, it is going to take longer time. Remember that it's all the exponential regeneration. So if the input is small, it is cool. So this is one way in which, one way to make this asynchronous SAR, particularly for the monotonic switching scheme. Okay. Yeah, basically we have to ensure that this capacitor is switched only after the first comparison is done. Similarly, the second capacitor should be switched only after the second comparison is done. If you don't give phi 1 and just give, let us say, D1, D1 can have some logic based on the previous conversion. It's a flip-flop, so it will store the previous conversion result. Based on that, you don't want to ground this. Fine? Cool. So one nice thing here is, if you look at everything that I have drawn in color, blue and green, so it's a NAND gate, inverters, OR gate, bunch of flip-flops, and even this fellow switches, right? You see I have a PMOS and MOS. Yeah, NMOS is connected to VDD, sorry, PMOS is connected to VDD, NMOS to ground. Gates of them are connected, drains are connected. So again, it should click a bulb. If you feel like it's a classic circuit, you have seen it somewhere. What is this? It's a CMOS inverter. This bunch of switches is also a CMOS inverter. So technically speaking, you can make a SAR ADC almost using only digital blocks. So the only, probably the analog portions are the capacitors here, this sampling switch, and how will you implement this sampling switch now? What are the options you have? This is sampling the input. This is continuously time varying. What can you use? Yeah, you can use gate bootstrap switch. That's the best thing to do. Or you can use a CMOS switch also. But gate bootstrap is, of course. So except this, and let us say comparator, even a comparator is a cross-coupled inverter. Inverters are disputed territories. Analog people claim it's theirs, digital people claim theirs. So here it is used in a kind of a both way. But you see that to make this, all you need is a bunch of digital blocks. So that's why as a modern circuit designer, it is not just enough if you just know how to make analog circuits. You should also be comfortable in making digital circuits like this. And especially in the case of SAR, the basic idea of SAR is binary search that people knew for like several long time. But for a really long time, people were doing SAR in a synchronous fashion like this by feeding a high frequency clock. But only later, some people realized we can do a smart thing using asynchronous digital logic, and then they came up with this. And this was not very old. This was probably in 2005-6. Around that time is when this was first introduced. And since this was introduced, the interest in SAR has exploded like anything. There's a whole bunch of work done in SAR. So much so that almost for all applications we try to use SAR, because as you see, it's a digital circuit. Again, all advantages you read in the first page, first paragraph of a digital IC textbook. will hold good here, right? And yeah, and even in all these, gigabits per second time interleaved ADCs we saw for this wireline applications, they interleave SAR ADC. So yeah, so that's why you should be comfortable in doing these things, and that's the beauty of mixed signal circuits. If you have a problem, you can either solve using analog or using digital. So I always say that is like being the middle child. You can get help from both your younger sibling and elder sibling, but it can backfire also, right? So here you might have problems from both analog and digital. So yeah, cool. So if this logic is clear, let's move on. So any clarifications on this? Basic idea is clear, right? The self-timing is basically this valid to reset. That is the self-timing happening so that you do this.
So while designing for the comparator,
Mm-hmm.
you decide upon its delay.
Delay, yeah, okay.
And delay will depend upon the differential.
Correct.
So
Typically, the best thing is you look at the regeneration time constant, right? I mean, you know that output for a small well it goes as e power plus t by tau. So gain, if you say V out by delta V in, it's a time varying gain which is e power plus t by tau. So the gain is predominantly determined by this time constant. So you keep it as small as possible.